The proposed subpanel installation design raises significant safety concerns. The design involves installing a subpanel with a 50-amp ground fault circuit interrupter, or GFCI, main breaker, using standard 1-pole 20-amp branch circuit breakers and installing standard receptacles. This setup is not advisable and could create potential hazards. Firstly, the main breaker should be sized appropriately for the subpanel's total load. In this case, for a 50-amp subpanel, a 50-amp main breaker is generally appropriate, assuming the load calculations support this size. Secondly, standard 1-pole breakers should not be used in a 50-amp subpanel in the manner described. The National Electrical Code, or NEC, and good electrical practices dictate appropriate breaker sizing based on the loads they serve and the capacity of the panel. Using a collection of 20-amp breakers in a 50-amp subpanel without considering the overall load and applicable codes can lead to overloads and potential fire hazards. Also, standard receptacles are not rated for 50 amps. Standard household receptacles are typically rated for 15 amps or 20 amps. Using a standard receptacle on a circuit capable of delivering 50 amps would be a severe safety violation. The high current could easily overload the receptacle, leading to overheating and potentially causing a fire. GFCI protection should be implemented correctly. While a 50-amp GFCI breaker offers some level of ground fault protection for the entire subpanel, it's not the ideal approach for individual branch circuits. GFCI protection is most effective when applied at the point of use, such as at the receptacle. This is especially true in locations where ground faults are more likely, such as bathrooms, kitchens, and outdoor areas. Here's a more detailed breakdown. Regarding the main breaker rating, the main breaker protects the entire subpanel from overcurrent. A 50-amp main breaker is typically used for a 50-amp subpanel. However, it's crucial to verify that the subpanel's total load does not exceed 50 amps. This involves calculating the loads of all branch circuits and ensuring they stay within the panel's capacity. When it comes to branch circuit breaker rating, standard 1-pole breakers can be used in a 50-amp subpanel, but their individual amperage ratings must be appropriate for the circuits they serve and the corresponding wire sizes. Using multiple 20-amp breakers might be acceptable if each circuit is designed to handle 20 amps and the overall load on the subpanel remains within the 50-amp limit. Each circuit's breaker size should match the ampacity of the wiring and the load it is intended to serve. Concerning receptacle type, standard receptacles are typically rated for 15 amps or 20 amps, depending on the circuit they are installed on. Using standard receptacles on a 50-amp circuit would be extremely dangerous. The receptacles must be rated for the appropriate amperage of the circuit they are connected to. For GFCI protection, a 50-amp GFCI breaker at the main panel provides a level of ground fault protection. It's more effective to provide GFCI protection at the receptacle level, especially in areas prone to moisture or where electrical equipment is used near water. This can be achieved by using GFCI receptacles or GFCI breakers for individual circuits. Now, let's consider a fault scenario. If a fault occurs on a branch circuit, the 20-amp branch circuit breaker should trip, isolating that circuit and preventing further damage or hazards. However, the 50-amp GFCI main breaker will only trip if a ground fault is present. A ground fault occurs when current leaks from a hot wire to a grounded surface. Without a ground fault, the 50-amp GFCI breaker will not trip, even if there's an overcurrent situation. This could create a dangerous situation where a fault is not detected and the circuit continues to pose a risk. In conclusion, the described design and installation is not recommended. It may not comply with electrical code standards and could lead to safety hazards. To ensure a safe and compliant installation, you should consult with a qualified electrician who can assess the specific needs of the installation and design a system that meets all applicable codes and safety standards. Proper electrical design involves careful consideration of load calculations, breaker sizing, wiring ampacity, and GFCI protection. It's crucial to follow best practices and adhere to the NEC to prevent electrical hazards and ensure the safety of the electrical system. Understanding electrical concepts is vital for anyone working with or around electrical systems. Let's delve deeper into some key principles that are relevant to this particular scenario. Firstly, we need to understand about overcurrent protection. Overcurrent protection is a fundamental aspect of electrical safety. It involves the use of devices like circuit breakers and fuses to automatically interrupt the flow of electricity when the current exceeds a safe level. This protects electrical circuits and equipment from damage due to overloads, short circuits, and ground faults. Secondly, we need to know about circuit breakers. Circuit breakers are electromechanical devices designed to protect electrical circuits from overcurrents. When the current exceeds the breaker's rated amperage, the breaker trips, interrupting the circuit and preventing damage. Circuit breakers can be reset manually, allowing the circuit to be restored after the fault has been cleared. Fuses are another type of overcurrent protection device. Fuses contain a metal filament that melts and breaks the circuit when the current exceeds a specified level. Unlike circuit breakers, fuses must be replaced after they blow. Ground fault circuit interrupters, or GFCIs, are designed to protect people from electric shock. GFCIs monitor the current flowing in a circuit and quickly interrupt the power if they detect a difference between the incoming and outgoing current, which indicates a ground fault. GFCIs are commonly used in areas where there's a risk of electric shock, such as bathrooms, kitchens, and outdoor outlets. Electrical codes and standards are sets of regulations and guidelines that govern the safe installation and maintenance of electrical systems. These codes are developed and enforced by organizations like the National Fire Protection Association, or NFPA, which publishes the National Electrical Code, or NEC. Compliance with electrical codes is essential to ensure the safety of people and property. The NEC is a comprehensive set of standards that covers virtually every aspect of electrical installations. It provides detailed requirements for wiring methods, overcurrent protection, grounding, and many other areas. Adherence to the NEC is mandatory in many jurisdictions. Now let's talk about wire gauge and ampacity. Wire gauge refers to the physical size of an electrical conductor, typically measured in American wire gauge, or AUG. The ampacity of a wire is the maximum amount of current it can safely carry without overheating. The ampacity of a wire depends on its gauge, insulation type, and installation conditions. Proper wire sizing is crucial to prevent overheating and fire hazards. A wiring system should be properly grounded for safety. Grounding provides a low-resistance path for fault current to flow back to the source, allowing overcurrent protection devices to trip and clear the fault. Grounding also helps to stabilize voltage and reduce electrical noise. There are several types of grounding systems, including equipment grounding and system grounding. Equipment grounding connects the metal enclosures of electrical equipment to ground, while system grounding connects the neutral point of the electrical system to ground. Load calculations are an essential step in electrical design. Load calculations involve determining the total amount of electrical power that will be used by all the devices and equipment connected to a circuit or panel. This information is used to size the conductors, overcurrent protection devices, and other components of the electrical system. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. Voltage drop calculations are used to determine the appropriate wire size to minimize voltage drop. Short circuit current is the high current that flows during a short circuit fault. Short circuit current calculations are used to determine the interrupting rating of overcurrent protection devices. The interrupting rating is the maximum amount of current that a device can safely interrupt. Now, let's consider how to apply these principles to the specific scenario. In the described scenario, the main breaker should be sized according to the total load of the subpanel. For a 50 amp subpanel, a 50 amp main breaker is typically used, but the actual size should be based on load calculations. The branch circuit breaker ratings should be appropriate for the circuits they serve and the corresponding wire sizes. Standard 1-pole breakers can be used, but their amperage ratings must be carefully selected. Standard receptacles are not rated for 50 amps and should never be used on a 50 amp circuit. Receptacles should be rated for the appropriate amperage of the circuit they are connected to. GFCI protection should be provided at the receptacle level, especially in areas where there's a risk of electric shock. This can be achieved by using GFCI receptacles or GFCI breakers for individual circuits. It is important to consult a qualified electrician. Electrical work can be dangerous and should only be performed by qualified individuals. A qualified electrician has the knowledge, skills, and experience to design and install electrical systems safely and in accordance with electrical codes. They can also perform load calculations, select the appropriate components, and ensure that the system is properly grounded and protected. There are several potential hazards associated with the described installation. Firstly, there is an overload hazard. If the total load in the subpanel exceeds 50 amps, the main breaker could trip, causing a power outage. Overloading can also damage the wiring and equipment connected to the subpanel. Secondly, there is a fire hazard. If the wiring is undersized or the overcurrent protection is inadequate, the wiring could overheat and cause a fire. Electrical fires can spread quickly and be very dangerous. Thirdly, there is an electrical shock hazard. If there's a ground fault or other electrical fault, people could receive an electric shock if they come into contact with energized parts. Electric shock can cause serious injury or even death. The design and installation described are not recommended and may not comply with the electrical code standards. It's crucial to consult with a qualified electrician to ensure a safe and compliant installation. Remember that electricity is a powerful force that can be dangerous if not handled properly. Always follow safety precautions and consult with qualified professionals when working with or around electrical systems. To elaborate further, let's discuss the importance of proper wiring methods. Proper wiring methods are essential for the safe and reliable operation of electrical systems. The NEC specifies various wiring methods for different applications, including the type of cable or conduit to use, the methods for supporting and securing the wiring, and the requirements for protecting the wiring from physical damage. Some common wiring methods include non-metallic sheathed cable, or Romex, which is commonly used for residential wiring. It consists of insulated conductors enclosed in a plastic sheath. Electrical metallic tubing, or EMT, is a thin-walled metal conduit that is commonly used for commercial and industrial wiring. It provides good protection for conductors and is relatively easy to install. Rigid metal conduit, or RMC, is a thick-walled metal conduit that provides excellent protection for conductors. It is typically used in harsh environments or where the wiring is subject to physical damage. Liquid-type flexible metal conduit, or LFMC, is a flexible metal conduit that is covered with a liquid-type jacket. It is commonly used in wet locations or where the wiring is subject to movement or vibration. Cable trays are open support systems that are used to support and route cables. They are commonly used in commercial and industrial facilities. The choice of wiring method depends on various factors, including the type of occupancy, the environmental conditions, and the voltage and current levels. Now let's discuss the importance of proper grounding and bonding. Grounding and bonding are essential for electrical safety. Grounding provides a low-resistance path for fault current to flow back to the source, allowing overcurrent protection devices to trip and clear the fault. Bonding connects metal parts of the electrical system together to create an electrically conductive path. This helps to equalize voltage and reduce the risk of electric shock. The NEC specifies requirements for grounding and bonding, including the size and type of grounding conductors, the methods for connecting grounding conductors to equipment, and the requirements for grounding electrodes. A grounding electrode is a conductive object that is buried in the earth and connected to the electrical system. It provides a connection to ground and helps to stabilize voltage. There are several types of grounding electrodes, including ground rods, ground plates, and metal water pipes. Ground rods are metal rods that are driven into the earth. Ground plates are metal plates that are buried in the earth. Metal water pipes can be used as grounding electrodes if they meet certain requirements. It is essential to follow the NEC requirements for grounding and bonding to ensure the safety of the electrical system. Another important aspect of electrical safety is arc flash protection. An arc flash is a dangerous electrical explosion that can occur when there is a fault in an electrical system. Arc flashes can generate intense heat and pressure, causing serious burns, injuries, and even death. Arc flash protection involves the use of personal protective equipment, or PPE, such as arc-rated clothing, gloves, and face shields to protect workers from the hazards of arc flashes. Arc flash studies are conducted to determine the potential arc flash hazards in electrical systems. The results of these studies are used to develop arc flash protection plans and to select the appropriate PPE. The NEC and other standards provide requirements for arc flash protection. It is essential to follow these requirements to protect workers from the hazards of arc flashes. In summary, the design described is not advisable and may create potential hazards. It's important to consult with a qualified electrician to ensure safe and compliant installation. Remember to follow safety precautions and consult with qualified professionals when working with or around electrical systems.